Okay, so welcome everyone. I'm gonna again join my session and myself and hopefully share my screen. So let's go ahead. Again, asks for a password from me. Uh, uh, oh, what's going wrong? Okay, let's say joined without video. Let's mute. I need to be co-host. Where is my name? Okay, so let's share our screen. Open this up. Okay. Okay, hold on a second. Okay, guys, you can pin my video. You can select my video and pin it. I don't know why I have... Bir saniye arkadaşlar. Şeyde bir... sesim bir yerden eko yapıyor ama nereden eko yapıyor? Şuradan mı? Bir saniye. Şunu yapmış olmam lazım. Galiba bunun pili bitti. O zaman şey yapacağız. Okay. All right, guys. So let's continue our discussion. We had started. Let me also check whether I have my recording going on. Okay, that's fine. So we had started talking about different types of mathematical models. So we will try to continue this with some examples, okay? So, and I will spend some more time on different examples. But let us do this, okay? Let us start with a very simple linear dynamic system. And let's also work on some different versions of this system, okay? So I'm saying example, linear dynamic system. Then what we will do is we will also find out about its discrete time version, okay? So this is linear dynamic system continuous time. So something you are very familiar with, and then we will move on to basically a very brief introduction to discrete time, but you will have during EE402, obviously you will have quite a bit more on this, okay? So here's the example. The example is basically a very simple RC circuit, okay? Where, remember, from 302 we have basically component equations, and we have also topological equations. Let's call this V, the input to the system. We have R and we have C, and obviously we have a single loop, therefore we have a single current flowing through this component. Now when I say dynamic, remember that we had already discussed that dynamic means defined by differential equations. Okay, so in this circuit, obviously this is a dynamic system, but there is also subsystems that are static. For example, you know that if I consider only the resistor, with the resistor voltage, we know that VR is equal to R times IR. Now this is a static system, right? Why? Because it is defined by an algebraic equation, okay? So you can't call this a static system. Obviously this is just a very small part of a bigger system involved, okay? So we model this from first principles by using component equations as well as the topological equations. What is the topological equation? It's the Kirchhoff's voltage law, right? I can write the Kirchhoff's voltage law along this loop. So I have minus V plus R times I. And here I have VC, right? Plus VC has to be equal to 0. Now minus V plus R times I, okay? Plus VC is C times dVC over dt. Now I have I here, okay? But I want actually a differential equation in terms of the capacitor voltage. Let VC be our variable of interest. Okay? So basically what I need here is that I need to what I'm saying is, okay, hold on. We have messed up here, right? So we have VC here, right? So what I have is that I can replace I. So I is equal to IC. It's also the current through the capacitor. And in fact, it's the current through the capacitor which is equal to the change in the voltage of the capacitor, right? So I can replace I by my variable of interest, which is in terms of VC, okay? So what I have here is that minus V plus R times C times dVC over dt plus VC is equal to 0, okay? Now I can write this, obviously I can, this is my input to this circuit. So I can rewrite this as RC dVC over dt plus VC. Remember, these are functions of time, right? VC of t is equal to V of t. Is a differential equation model. Differential equation model. So it's a dynamic system. It is a linear system, and you can prove it by applying the principle of superposition, whether it holds or not. And I can obviously also move on to the Laplace domain if I want to develop a frequency domain representation. So Laplace transform with initial rest assumption, okay? So in that case, I have RCS VC of S plus VC of S is equal to V of S. Normally, you know that the derivative of a variable is S times that variable in the Laplace domain minus the initial condition. So because the initial condition is equal to 0, we can omit that from this equation. So I have RCS plus 1, plus 1 times VC of S is equal to V of S, okay? And basically what I can write is that my output variable VC of S is equal to 1 over RCS plus 1 times V of S. And if you want to obtain the transfer function of this, T of S is by definition the output variable VC of S over the input variable in the Laplace domain. And that gives me the transfer function representation. RCS plus 1 is the transfer function representation of this system. Okay? So now let's also talk about how to find a discrete time approximation. What is the discrete time approximation? It is when you don't have the continuous time, but you only measure the values of the variables at equally spaced instants of time. Okay, so let's say that the sampling period is equal to t. Okay, so that means, in fact, what I'm doing is that any variable, for example v of t, becomes actually simply discrete instants of time, okay, that are separated by the sampling period t. So how can I obtain a discrete time representation? Okay, it is by approximation of the derivative that I can obtain this representation. Obviously, every variable that I am concerned about has to be now evaluated not at everywhere in time, but at discrete instants of time. Okay, so let me name also this. Okay, so an approximation is discrete time approximation. What I will use is the simplest way I can do this, and that is known as Newton's difference quotient. Okay, so the way to do this is the approximate the derivative. Okay, dv of t over dt, v of t being any one of our variables, but in this case it's going to be the capacitor voltage. Okay, so we will approximate this by a finite difference. Remember, it's the definition of the derivative. The derivative is actually defined with a limit where you have a difference, but the interval you take that difference is actually vanishing. That means the limit of the sampling period goes to 0. Okay, so we can make an approximation by getting rid of the limit, but simply assuming that this interval is very small. So I'm gonna have a difference of the voltage. So the value of the voltage at t plus the period minus v of t divided by that interval t. Okay. So and the time has to be taken at discrete multiples of the sampling interval. Okay. So that becomes v at k plus 1 minus v at k divided by t. You see, by letting t become simply a function of k and a constant, I can actually drop t dependence. I make the signal dependent only on the discrete time variable now, k. K becomes the discrete time variable. Okay. Now, one problem with this particular approximation is that this is not causal. Okay. In fact, the derivative operation is not a causal operation. Why? Because you are at time k, t, but you need the value of the function at a future time k plus 1 times t. Okay, so this is not causal. So a causal approximation, because so for this approximation is for t small, capital T small, and if capital T is very small and the function is continuous, this difference is also approximately equal to a causal version. The causal version is simply Vk minus Vk minus 1 over T. So we shift, the interval by one time step. If the function is continuous, it doesn't matter because the values are very close to each other as long as capital T is very small. Okay? Now, then our continuous time model, continuous time differential equation becomes I write my differential equation, which I had over here, right? In here, at the beginning of the next page. And I just replace the derivative operation. So what I have here is that RC, and instead of dVc over dt, I have Vc k minus Vc k minus 1 divided by my interval, sampling interval t, plus Vc at k is equal to V of k. Okay, so everything becomes a function of the discrete time, plus we no longer have a derivative operation. We just have a difference instead. Okay, so let me write that down. Let me multiply by t. So I have RC Vc k minus RC Vc k minus 1 and plus t times Vck has to be equal to t times Vk. Now what I can do is now write the value of my variable of interest Vc at time k in terms of its past values. Okay, so Vck becomes Rc over Rc plus t Vck minus 1 plus t over Rc plus t V of k. Okay, so that becomes an equation, and we call this a difference equation. Difference equation. It is essentially a discrete time system model. Okay, you see, this is a computational formula. To compute the next value of Vc given the previous value of Vc. That means at time k minus 1 and the current value of the input. So that means this difference equation, if you start with an initial value for VC and you know all the values of the voltage at future values, you can actually successively calculate what's going to be the value of VC at any future time. Okay? So this is really very suitable for kind of computer implementation, because it's simply a calculation formula. Okay, given VC at time 0 and all values of Vk for k larger than or equal to 0, all VCk can be calculated. Okay. Now the behavior of VC at time k or the VC at times kt in continuous time will approximate VC of t from the differential equation model, provided that, and you guys fill in the rest, right? Can somebody tell me what I have already said and what I need to write here? Yes? Are you guys still with me? Yes. Who is speaking?
This is Özgür. I guess the sampling period T must be small.
Capital
T is small.
Capital T is very small. Okay. So this approximation becomes more and more accurate as capital T becomes smaller and smaller. And in fact, if capital T is very small, this approximation is quite accurate. But if T becomes not that small but small, you need to actually resort to better approximations for the derivative, and in fact better ways of representing the discrete time version. And I guess most of EE402 or part of EE402 is about what kind of better approximations you might have. Okay. Any questions at this point? Now, let me also make a remark. Now, discrete time models, okay, so note, discrete time system models can be obtained by or as approximations to continuous time models, approximations to continuous time models, the way I have illustrated, but also may naturally arise from discrete time physical processes. Some processes, let's say stock market, okay, are naturally discrete time. You don't need to discretize a continuous model, but it's already given in terms of difference equations. Okay? Any questions so far? Now I have another example illustrating a nonlinear system that we will often deal with in this course. But before that, I want to kind of go over my small exercise for this session. Is everyone kind of online and ready to go? Now, please go ahead to our course website. In this week's schedule, I'm going to make our exercise visible. Okay. Now I'm going to go in and let's finish this. So I will open up our session. You will probably need to refresh your page after I start the session. So I'm starting this exercise. Please reload or re-enter that area and you should be able to see the single question. There is only one question. It's a multiple choice question. Are you able to see and answer the question? Okay, looks like it. Hopefully, I will have no wrong answers on this one. Oh, somebody has jumped into... remember, I believe you have another try if you want to retry your answer.
Ya hocam ben yapamıyorum. Bir sorun çıktı ODTÜ anlamadım.
Şey yapalım. Tekrar bir reload edin şeyi, quiz'i. Sonra düzeltiriz olmazsa. Şey yapalım, dersin sonunda kalın. Sizin cevabınızı düzeltelim, olur mu?
Olur hocam.
Tamam.
Ben giremedim soruya falan.
Tamam, anlaşıldı. Ders sonunda hatırlatın, olur mu? Çıkmayın.
Tabii hocam.
Tamam. Bu arada birkaç tane sanıyorum ki 3 tane yanlış cevap var. Bir arkadaşınız it can be obtained by approximating the derivative operator by a finite difference. Buna yanlış dedi. Temelde bu doğru çünkü hani biraz önce yaptığımız şey tam olarak buydu yani. Derivative işlemine biz bir finite difference approximation'ı yaptık. O şekilde devam ettik. Bir arkadaşınız it well approximates the continuous time version as long as the sampling period t is small'la yanlış dedi. Biraz önce hani bunu konuştuk. Sonuçta capital T küçüldükçe bu discrete time sistemin sample'ları continuous time sistemin VC of T'sine mesela yaklaşacak. Bu şekilde söyledik. Bir de it can be analyzed in frequency domain using Z transform. Bununla ilgili bir şey söylemedik. O benim hatam. Çünkü bu modeli aslında Z transformunda alacaktım. Onu unuttum ama hani zaten 402'deki büyük bir eforunuz Z transform'la da geçecek. Temelde difference equation'larının frequency domain representation'ı Z transform. Şimdi yapıvereyim onu. Ama hani bu arkadaşlardan özür diliyorum. Hani Z transform'dan hiç bahsetmedim. Aslında bahsedecektim yani planım oydu. Biraz erken oldu diyelim. Başka sorusu olan var mı? Şu şeyi göstereyim size. Şöyle yapalım. How to represent the discrete time system in frequency domain. okay, is through the Z transform. So the way we do this is, again, we assuming Vc at time 0 is equal to 0, essentially we can write this entire difference equation in a Z domain. In this case, the delay operator, you see when I have Vc k minus 1, it's a one time step delayed version of Vc of k. So the delay is represented by z to the power minus 1 in Z domain. So I have Rc over Rc plus T Vc Z plus T over Rc plus T Vz. So instead of time delayed version of a variable, now I have the same variable. So I can write again an algebraic equation. So I regroup Vc of z on the left hand side. 1 minus z to the minus 1 Rc over Rc plus T Vc z is equal to T over Rc plus T V of z. And therefore I can actually write the transfer function in terms of the z transformed versions. So I have T over Rc plus T divided by 1 minus z to the minus 1. Again, Rc over Rc plus T times times nothing, basically. This is our transfer function, right? Okay. So the Z domain transfer function. Okay. All right. So let me go over another example for you. Let's say example, a nonlinear dynamic system. In fact, this, nonlinear systems are the topic of, for example, 404, at the graduate level 555, and also next term EE406. We will deal with a lot of nonlinear systems, and this particular system is in fact occupies a big chunk of 406 because we have experimental setups that resemble this system. This is basically a pendulum system, and we will use a very simple interpretation of this system. So let's see what we have. We have a pendulum. Okay, let me try to draw it somewhat meaningfully. A mass is being suspended from a rigid wall. There is a rod of length L. It's not flexible, so its length is constant. So we have the angle theta from the vertical, and we want to develop a differential equation model of the system. We have gravity acting on the mass, mg. Okay, so what happens, we know what's going to happen, right? This system will basically have, if there is no friction involved, and I'm going to omit the friction in this example, if we leave this with an initial energy and with an initial condition, it's going to keep swinging. It's going to have an oscillation that is not dying. Okay, so this oscillation will be governed by a differential equation, and we want to find out what's that differential equation. Okay, so let me try to work this out for you. So we have gravity here. Part of that gravity will be acting along this rod, but the rod is not flexible, so nothing happens. So this component, because this is angle theta, this is mg cosine theta. this component of the gravitational force does not work because there is no motion along length L, okay? But the other component, this one, which is mg sine theta, will be actually moving this mass along this trajectory, along this circular trajectory. So I want to, in this example, I want to use Newton's second law, with linear motion. So I know that I have F net has to be equal to m times acceleration, but acceleration has to be along this motion path, okay? So this is our x direction, okay? In fact, this is our x direction, right? This in terms of the sign, okay? But unfortunately, basically I need to come up with an equation in terms of theta, because theta is my variable of interest, okay? Theta is the variable of interest. So I want to integrate a relationship between this linear motion along this circumference and variable theta, okay? And I know an arc length, okay? So we know that I have the travel distance is equal to L times theta. Therefore, I can also write the derivative of x is L times the derivative of theta. And similarly, the second derivative is L times the second derivative of theta, because L is a constant, okay? Okay. Now I can, so what is F net on this mass, okay? F net, which is causing the motion, is equal to m times g times sine theta, and that is equal to m times x double dot, but this is equal to m times L times theta double dot, okay? So I have ml theta double dot is equal to essentially mg. Sorry, I have okay, so I have a sign mistake here, right? So you see, if I move in the x direction, the positive theta direction, the positive x direction, the force acting on this mass is in fact in the negative direction, right? It's opposing basically positive x and positive theta. So I have F net is equal to minus mg sine theta and minus mg sine theta, okay? So if you want to write this as a differential equation directly, so what you have is m times L times d square theta of t over dt square, the derivative, second order derivative, plus g times sine, sorry, I'm cancelling here, okay, plus mg sine theta is equal to 0, okay? And you see that I can cancel out masses, so the dynamics of this system, right, the dynamics, that means the behavior of this nonlinear system is independent of m, okay? So this is my differential equation representation of this nonlinear system, okay? Can I obtain, guys, a transfer function representation for this system?
No, we can't.
Who is speaking?
Özgür.
No. Right?
Transfer function is only suitable for linear systems.
Linear systems, right? Only for linear systems. Can I develop a very simple linear approximation to this system? I guess we can. can we find a linear approximation? And what is the assumption that we can use for that? Any ideas?
For small values of theta, sine theta is equal to theta.
Okay, very good. Who is speaking?
Atakan.
Atakan. Okay, so yes, right? For very small theta, sine theta is in fact approximately equal to theta. Okay, why? Because we know how sine works, right? Sine goes like that, and for very small theta, so this is theta, this is sine theta. If you're within this region of very small theta angles, in fact, you can approximate, you can make that approximation, and in that case, your differential equation becomes L times d squared theta of t over dt plus g times theta of t is equal to 0. And now what I can do is I can take the Laplace transform with the initial condition assumption. Okay, so I have Ls squared theta of s plus g times theta of s is equal to 0. Okay, can I actually obtain a transfer function here?
Yes, we can.
I guess we can't. There is another problem here. What is that?
There's no input.
There is no input, right? So there is no input because, you know, obviously you can take gravitational acceleration as the so there is no input in this system, right? This is a what we call an autonomous system. Okay, a system with no input. Okay, so we can, yes, we can write this equation in the Laplace domain. So I can have Ls squared plus g times theta of s is equal to 0, but no input to this system. Therefore, no transfer function representation. Okay, obviously we can easily fix that. For example, I can introduce a torque to this at the joint, in which case you know, my equation will be equal to the input torque, and that's going to make it possible to obtain essentially a transfer function. Okay. All right. Any questions?
Hocam şimdi bu sistemde input yok. Initial conditional rest aldık. Hani initial rest'i aldık. Hani bu şekilde başlayabiliyor oluyor mu?
Başlayamıyor. Aynen öyle. Yani dolayısıyla şöyle initial condition'ı yani initial rest almaya neden ihtiyacımız vardı? Sadece Laplace domaine geçmek için. Ama burada Laplace domaine geçmenin de bir anlamı kalmadı. Çünkü zaten transfer function tanımsız, input'u olmayan bir sistem için. Dolayısıyla elde ettiğimiz Laplace domain equation çok anlamlı bir equation olmadı. Değil mi? Yani bu sistemi initial condition'dan analiz etmek için sonuçta differential equation'ını bir initial value problem olarak çözmemiz lazım.
Anladım hocam. Teşekkürler.
İsterseniz şöyle yapalım. Az bir vaktimiz var. Şöyle diyelim. In order to have a TF representation, define let's see ama o zaman biraz karışacak, çünkü ona girmeyelim. Çünkü tork tanımlayacağız. Fakat biz kuvvetler üzerinden denklemimizi yazdık. Sonradan theta domainine çevirdik. Halbuki sistemi torklar üzerinden yazsaydık o zaman daha anlamlı olacaktı. Peki şöyle yapalım. Define an input torque at the joint. Okay. In that case, what you will have is that your equation will become okay. So bu durumda şöyle de olmayacak tabii ki. Şöyle yapalım. ml d square theta of t over dt square plus m times g sin theta. Onu basitleştirdik, şey yaptık. M times theta yaptık. Pardon, m g theta is equal to torque of t. Okay, theta of t, torque of t. Şimdi Laplace domaine geçersek ml s square theta of s plus mg theta of s is equal to torque of s.
Hocam tork böyle kuvvet kolu gibi bir şey olması gerekmiyor mu? Force'a dönüşmesi için.
Bence olabilir. Bir de tork hocam üstteki yerden uyguluyorsak ipten tork geçmez zaten.
İp demedik ona, rod dedik ama.
Rod mu?
Evet, rod dedik. Ama şu yaptığım yanlış olabilir. Çünkü normalde bunu tork üzerinden modelleyebiliriz. Öyle yaparsak daha güzel olacak, şık olacak. Şey yapalım. Buradaki zorluk şuradan kaynaklanıyor. Input'u biz tork olarak verdik. Ama sistemi force üzerinden çözdük. Alternatif olarak şöyle yapabilirdik. O zaman daha anlamlı olacaktı. En azından torkun olduğu. Şurada bir tork input var. Bu arada tork input'u da şöyle tanımlayalım madem. Tork input olsun. L olsun. M olsun. Burası theta olsun. Okay. Burası mg olsun. Şurası mg sin theta olsun. Fakat denklemimizi şöyle yazalım. Net torque eşittir inertia çarpı angular acceleration olsun. Şimdi burada da şuna ihtiyacımız var. J nedir? J
ml square.
aynen öyle. J equals ml square for a system with a rod of length L. Yani bir noktasal kütlenin belli bir nokta etrafında ki inertiasını hesaplamak için onun kütlesi çarpı aradaki mesafenin karesi olması gerekiyor. Dolayısıyla ne olmuş oluyor? T net is equal to applied torque T of T değil mi? Minus mg sin theta times L. Çünkü bir kuvveti L kolu üzerinden buraya uyguladığım tork kuvvet çarpı moment kolu olmuş oluyor. Eşittir J, which is m times L square times theta double dot. Okay. Now you have another differential equation where you have ml square d square theta t over dt square is actually equal to torque of t minus mg sin theta of t. Sorry, mgl sin theta of t. Okay. Now you can do the same, right? You can say this is approximately equal to theta of t, and now you have so that is for you obtain the new transfer function. Okay, and let's kind of get rid of this part. Okay. So if you have an input torque and you want to model the system in the domain of rotational angle, you can actually project everything to the rotational domain, and you can model it as a rotational dynamic system by using the Newton's second law of motion in the rotational domain. Okay. Soru var mı arkadaşlar? Peki arkadaşlar, teşekkür ediyorum. Bir arkadaş için şeye bakacaktık.
Evet hocam ben...
Tamam. Diğer arkadaşlar çıkabilirler. Görüşmek üzere arkadaşlar haftaya.
Hocam ben bu dersle ilgili değil de genel bir şey soracaktım.
Tabii sorun.
Dersle ilgili hani net bir kitaptan takip etmiyoruz ya, birkaç kitabın kombinasyonu
Evet.
şeklinde.
Aha.
Örnek problem görebileceğimiz bir materyal önerebiliyor musunuz?
Verdiğim referanslarda örnek problemler var. Derste de bir takım problemler çözmeye çalışacağız.